recording this board just again. Just so on the video. Of the summary of what we did about a week ago. So there it is. I'm going to wash it. It's going to go away. Okay, now what I stated was we have this object. There you can see it. It's not, if we look at it on this face, if this is part of a graph, we see there's a little upward slope here relative to the axis. If the axis is across the bottom here, this thing is sloped a little bit in this direction, okay? And if I look over here, it's clearly got a slope in this direction. Now, what I said was, this point is going to be in the XY plane. So this is your point XY, okay? Then, if the x-axis is in this direction, y-axis is in this direction, so that the y-axis is 90 degrees counterclockwise from the x-axis, as it has to be a right-hand coordinate system. It's my right hand there. Okay? Then, if this distance is delta y, okay, this distance here, then this is the point x, y plus delta y, right? And this point back here, I'm pointing to, is in the x direction. It's x plus delta x, y. Now, delta x would be negative, but it's still plus delta x. When you write x plus delta x, you don't know if delta x is positive or negative if you haven't specified it. Okay? So the way I have the thing oriented, the way I originally stated the orientation, your delta y would be this way. And be positive, your delta x is in this direction, and that's opposite the x direction, so it's negative. Okay, so we won't quibble too much about that. But what I asked then was, I gave you a ruler and said, tell me what f of xy is. Okay. Now most people went ahead and measured this because that's what f of xy is. I think I said right there is f of xy. Then I said, take the measurements you need to find the slope. Okay, of this segment right here. Okay, so it's like, I'm saying a little more than I did originally. It's like this is a section cut out of a quadratic surface or something, or the graph of some function f of x, y. Okay, then this slice is with a plane perpendicular to the x-axis. So it's in a plane parallel to the YZ plane. And this slice is in a plane parallel to the XZ plane. So now we're assuming that we confine ourselves to this YZ plane through the point XY, and we're calculating a slope. Okay, which is going to be an approximate partial derivative. Just give you a little heads up because that's going to be your assignment this week. Okay. And then we can make measurements here. This is our x direction along here. Okay. We make measurements to determine this slope. All right. Now, then I ask people to draw, introduce the picture, then label the picture. And people were doing various things because it takes a little while to get oriented to 3 dimensions. And it's useless to talk about partial derivatives if you're not oriented to 3 dimensions. And if you are oriented to the 3 dimensions and this exercise here, then partial derivatives are pretty easy to understand, as are normal planes and so forth. The only thing that's not easy to understand is what happened to the piece of chalk I was writing with. And I got a problem with my fingers, so I kind of need one. Oh, move something. Okay. So here's a picture as I specified it. Now, some people decided that XY was here. Okay, you can do that. If this is XY, then this would be XY plus delta Y. Okay. Now your delta Y would be negative if your XY was here. Okay. That's okay. And people eventually got that straight, okay? And then you'd be measuring this slope and this slope here, okay? And this point would then be, if this was xy, this would be x plus delta xy. And your delta x would be positive, your delta y would be negative. Some people even chose the back corner as the xy. They got that right. You know, and this would be x plus delta xy, this is xy, and this will be xy plus delta y, that corner, okay? Now, if you want to measure, I'm going to go with the orientation I started with, but you can adapt everything to whatever orientation you use, and you can even think, okay, well, if I'm letting this be xy, then how would I label my picture, okay? Now, f of xy, I even stated it, it's the z coordinate. Well, you know, here's the base, z coordinate goes this way. Here's the point xy, here's f of xy. It's represented by this arrow that goes from the xy plane up to the surface at that point. And here would be, again, with my orientation, let me use a little color here. Okay, so just to make it completely unreadable. Okay, this arrow here represents f of xy. This arrow represents f of x, y plus delta y. Then we could have an arrow back here. That's f of x plus delta x, y. And we could even have an arrow back here. It could represent f of x uh-oh. I didn't label that right because I was thinking somebody else was labeling. This would be actually the longest one in the least space, but f of x plus delta x. Y plus delta y. Okay, that would be the arrow corresponding to this back corner. And this is f of x plus delta x y. Okay. Make sense? Now you should label the whole picture, depending on where you did it. And if you did it with this orientation, change your orientation. Let x, y be one of these other points. Just see how it looks out. Okay, you know, keep the x direction this way and the y direction this way. But just as a good exercise, we'll do it in some different orientation. Okay, so you're sure that you can think of this relative to the particle orientation. So let's just make sure that we understand that's this one, and this is this one. Okay. Now, what's the slope? Well, people took measurements. They got numbers for this. First of all, usually these distances are about 3.5 inches. Okay. Because this is 4x4 lumber, which really makes 3.5 by 3.5. Okay. Probably not exact. Again, everybody seems to have chosen to measure these things in inches. You'd be more precise to have measured it in centimeters because you have your millimeter marking is smaller than your 1/8 of an inch marking. And I think 1/8 of an inch is the smallest marking you have. That could be wrong. Yeah, it doesn't. Okay. One of those rules is micro. That's what's going to use. But still, decimals are kind of easy to work with the fractions. On the other hand, fraction is sometimes the exact thing. So if you're wanting precision, millimeters is better than eighths of an inch. Okay, we have about 3 millimeters in eighths of an inch. Got 3 times. Then let's just take this face here. This face is point x, y. Here's the point x, y plus L of 1. Here's f of x, y. Here's f of x, y plus L of 1. And maybe this is 3 5/8 inch, and this is 3 4 inch or whatever, okay? Now, some people were measuring along here. I saw a lot of rulers along a slope. If you want a slope, you better use delta y, which is from here to here, not from here to here. Now, these are all pretty small slopes. It wouldn't be too far off with that. Just if you're inclined to do that, hopefully you're no longer inclined to do that. But if you are, become less inclined to do that and use the delta y, because now the slope and this is the average slope because some of these things are a bit curved. Now with a cutoff saw, it's not that easy. And it's pretty dangerous for an old guy like me to be cutting curves. Okay. If I had a bandsaw, I could do a lot of neat stuff. I've got one, but it's disassembled and I can't seem to get the saw back on it. I don't have room to work on it. So anyhow, there's your average slope. Does that make sense? Okay, well, this is a slope. It's an average slope due to change in y. Okay. Now, if the thing is curved, there's an instantaneous slope at this point. And if we have the equation of the functions, we can let delta y break to 0 and take the average slope. Okay. And we get closer and closer to the instantaneous slope. So I'm just going to state, and you can digest this. I'm just going to continue my steps out here. It's the limit delta y approaches 0 of the average slope, which is just f of x plus delta x or f of x y plus delta y minus f of x y over delta y. Okay. And there should be no mystery in that. That's almost exactly like the difference quotient that you learned a year ago in calculus. Took calculus last year. Okay. It's the foundation of your whole calculus course. And if you lost the forest for the trees and forgot where it came from, it's time to reintroduce yourself to the idea of what a derivative is. Okay? And this has a name. Instead of a d dy, we use this partial derivative sign, okay? To distinguish it from a derivative of a single valued function, okay? Now we could have a function of two variables, an f of x, y. In your homework, you encountered some functions of three variables, f of x, y, z. We could do a function of 38 variables. We'd probably call it your variables x1, x2, x3 up through x38 or something like that. Okay, or E1 through E38, because that's a notation you see in linear algebra. Not sure what your current text does, but that's a pretty standard notation, E1 through En from set basis vectors. Okay, so anyhow, there's a partial derivative, and it's just the limit of what you get here. If you wanted, if this was more curved, you could do an average slope between here and here. Everybody got, I think, good average slopes. Okay, at least one good average slope, and could have gotten another one if you had a little more time. We already spent 40 minutes in that exercise, so had to cut it short. But you understand, you measure the height here, you measure the height here, there you got it. If this thing's curved, well, you could measure the height here and here, let's say, okay? Or you could measure here and 3 nanometers to the right. 3 nanometers being about 30 atomic diameters, okay? And you can't really measure that. Okay. Hey, you got a good scanning electron microscope, know how to use it. I don't know. You know, we were offered one back, I don't know, 30 years ago. Guy who was originally the physics guy here is an engineer, and he went out, got an engineering job at one of the place. And they had an scanning electron microscope that they were going to donate to us. I said, thanks, but we got limited space. And take me a while to get up to speed, although I certainly do want to do that at other places. This is not practical, so thanks, but so I've never really regretted that. Would have been neat to have. Okay. Now, forget the digression. Do you understand what I'm saying here? It's just you keep making more and more precise measurements until you get down to measurement that's as close as you think you want it. Then you got a pretty good approximation to the partial derivative. If you have a formula for the function, and it's a formula that you can operate the limit on, like it's continuous and continuously differentiable and all that stuff, or at least differentiable. Okay, then you have this situation, and that's the definition of a partial derivative. When you got symbols, well, your text is going to have symbols. You're only good with symbols. Hopefully going to be good with limits. Okay, because we spent a lot of time with that, and we're not going to have a whole lot of time left to do a lot of examples with functions. We'll try to do at least one. Okay, so there's our definition. It'd be obvious how you write out this limit. If you had a little more time, I'd ask you to write it. See. notation. But it looks the same as this, except you're gonna do it delta x because you're running the x direction, right? Okay, now. Given the slope that you got, whether in the x direction or the y direction, tell me what the vector is. Give me the components of a vector. This is a vector. This is a vector, right? If top is a plane, then these vectors are both in your plane. In which case their cross product is normal to the plane, so you can easily write the equation. That makes sense? And we're doing equations of a plane. Equation of a plane normal to these two vectors through this given point, right? Well, you've got a point, it's x, y, f of x, y, and you've measured those things. Now I didn't tell you what x, y is. You make up any numbers you want for x, y if you really want to. But you really don't need the coordinates of x, y. What you need is just these two vectors and the so just a vector from this corner to this corner, from this corner to this corner, from this corner to this corner, if you chose your x, y here, and from this corner to this corner, that's where you chose your x, y, and all that stuff, right? Give me at least one of those vectors. You can do one of them, you can do the other. And try to do that fairly quickly. You don't have to do all the calculations necessarily. Just show me the numbers that you would use and how you would use them. Okay, some people might be having a little trouble getting started here. But just for example, if these are the 2 points, 4, 7.5, 12, 4, 4, 8, y changes from 4 to 4, 7.5, that's 3.5 inches, and that's what you use. But maybe things a little taller, 8 inches tall here and 12 inches tall there, right? Then what's the vector from, let's say, from this point to this point? Well, that vector is 0i minus 3.5 j minus 4k, isn't it? X doesn't change. So the x component is 0. Y goes down by 3.5, so that's negative 3.5 j. X dot k, z goes down by 4, so it's negative 4k. If the points were x, y, 12, as they might be if you choose your x, y as that lower right-hand corner. And this point was x, y plus delta y 8. What would the vector be? Then the vector t still 0i delta yj minus 4k, right? Now, if delta y is 3.5 or negative 3.5, then you'd have a negative 3.5 here as you could have here. Your x still wouldn't change. You'd have that vector. There's a vector, corner to corner. And that vector is approximately, and maybe exactly, all in the plane of the top. Now you can get two such vectors. Get one here, one there. Take the cross product, you get the normal. Okay, so I've asked everybody to do at least one of these two vectors with caveat for, because this is your corner or this is your corner, you know. But you're going to get two vectors along perpendicular planes. Perpendicular vertical planes. And if the top is flat, which it isn't in every case, but if the top is flat, then those two vectors are in the plane and you take their cross product and you've got a normal vector. And since you've got three coordinates, or if you have three coordinates of the point, X, Y, then you can get a normal, you can get the plane. You get the tangent plane. And the tangent plane is a big deal. And I don't think you're even going to be asked for a tangent plane in this assignment, because I'm only going to give you two sections to do, section 2 and section 3. Okay? Because we want to really establish the idea of partial derivatives, but I'm also going to say optional. If you want to really see where this is going, take a look at section, which I think is tangent planes. And if I'm wrong, well, but that. Okay, now let's calculate one. If f of x, y is this function, then the partial of f with respect to x is really easy to calculate. Now you want to really tune in on this. I'm only going to say it once. Of course, your book's going to say it, and it's easy. Okay. If you're moving in the x direction, y is constant. Okay. So we treat y as a constant and we just do the derivative with respect to x. Get that? If we're moving in the x direction, which is what the partial derivative of x does, y isn't changed. Y is the same here as it is here. It's the same here as it is here, or here as it is here, right? Y is constant. Then the partial f with respect to x is 2xy cubed, which is what I get if I take the derivative of x squared y cubed, treating y cubed as just a constant, minus 1 over y squared. Because treating x as a constant, the 1 over y squared is just a constant coefficient. Now, this is really easy. Nobody ever has any real trouble with this unless they just didn't learn anything with calculus. Okay. Now, maybe you have trouble with some of the functions they give you derivatives of, but you shouldn't be having trouble with power functions. Okay. And if you are, well, review it because you're going to have to do a lot of derivatives. Okay. And you're going to get pretty good at it. Okay. Partial def with respect to y. What do you think we do? Well, we're talking about now this picture, this part of this face of the y. Okay. And x is remaining constant. X is the same here as it is here, but y is changing. So the partial derivative is just going to be what we get if we treat x as constant, take the derivative with respect to y. Now I'll do this. But so I'm thinking of this x over y squared as an x times reciprocal y squared. And the derivative of the reciprocal y squared is negative 2 over y cubed. Now you can probably just cut through that and see pretty clearly you're getting 3x squared y squared minus 2x plus 2x over y cubed. Okay. So taking the partial derivatives is easy. Assuming you have a function that's easy to take derivatives of, because I can get pretty hard. Still, derivatives are not difficult. Get tedious, they can get long, you can get stake from. That doesn't make them hard to do, it just makes it hard to do accurately over many steps. Okay, it's really easy. Let's move on. Okay. Vectors tangent to the graph of this function. At the point, I'll say x naught, y naught, f of x naught, y naught. You see that? Sure. Not going to take too long to do this. And this is something that I don't necessarily expect that you'll have complete command of by next time. But if you do, it'll be your benefit. Still won't go over it more slowly. Let's say at the point two, f of 1, 2. So it's like now, here's the point 1, 2. You got some surface up there that your graph of the function in 3 dimensions. Okay. Then you got the point 1, 2, f of 1, 2, which is 1, 2, and f of 1, 2, 2 cubed is 8 times 2 is 16. That's going to be 16 minus 1 over 114. So it's no, I did perfect. It's 32 minus 1/4, 31 and 3/4. For this function, that would be the coordinates of the point. Okay. Let this be the vector in the y direction. Okay. That would correspond to this vector here. I'm just going to draw the picture. You go 1 unit and you go up partial f with respect to y. And what's this vector? It's one unit this way, partial f with respect to y this way. It's I, sorry, it's j. Got to go in the j direction. And the slope is partial f with respect to y. Okay. So you like this triangle, and it's j plus partial f with respect to y times k. Now you can put numbers in, just evaluate partial f with respect to y with x equal 1, y equal 2. And you get a number here, so you know what this vector is. And then in the other direction, And I'm going to relabel this. I'm going to call this the J vector. See what in the J vector. And that's partial with respect to y times the K vector. And right there is a vector that's tangent to the plane, assuming everything is okay. So if you don't see that, ponder it. And then the other vector would be like in direction of the I vector. So we have the I vector here. And partial f with respect to x times the K vector. So right there is the vector, which would be I plus partial f with respect to x times K. If you take the cross product of these two vectors, which is very easy to do, you get the normal vector. You've got the point on the plane. You can find the equation of the tangent plane, which approximates the behavior of the actual function. If you're close to the point x, y, f of x, y. Okay. Now that's a mouthful. Don't have time to expand on it because I'm already a couple of minutes over. People got to go to work and stuff. So yeah, replay that little part of the video and think about what I just said, because it'll give you a good head start on a later assignment. Okay? And we'll be going over it next week.